In today's video, we're going to take a look at hydrocarbons, and specifically at alkanes. First though, it's worth understanding that this whole area of chemistry is known as organic chemistry, which just means that it's all about compounds that contain carbon. You'll see over and over again in chemistry that carbon is a really useful element for making large compounds, because each atom of carbon can form 4 strong bonds, with the most common atoms to be bonded to being either other carbon atoms or hydrogen atoms. Now, lots of molecules only contain these 2 elements, and collectively we refer to all of these molecules as hydrocarbons, which we can define as any compound that's formed from carbon and hydrogen only. So this molecule, which is called butane, is a hydrocarbon, but this similar molecule, called butanol, isn't a hydrocarbon, because it also has an oxygen atom. The most simple type of hydrocarbons are a group called alkanes, and you need to know the first 4 in the series. The smallest is methane, which contains just a single carbon atom bonded to 4 hydrogens, because remember, carbons always have 4 bonds. Then we have ethane with 2 carbons and 6 hydrogens, propane, which is C3H8, and butane, which is C4H10. Now, if you look at all of these compounds, you'll see that they grow by 1 carbon and 2 hydrogens each time, but otherwise they're pretty much the same. We call groups of organic compounds like this homologous series, and it means that they all have similar properties, and so react in a similar way. It also means that we can write a general formula, which describes the entire series, and in the case of alkanes, the general formula is CnH2n plus 2. This might look a bit complicated, but all it means is that if the compound contains n carbon atoms, then it will contain 2 times n plus 2 more atoms of hydrogen. So if we had an alkane with 3 carbon atoms, like propane, then n would be 3. So it would have to have 2 times 3 plus 2 hydrogen atoms, so 8 hydrogens, which would give it the formula C3H8. Now, you only need to remember these first 4, but you could be asked to use this general formula to work out the molecular formula of much larger ones. For example, octane is an alkane with 8 carbon atoms. What is its molecular formula? Well, we know that for octane, n will be 8, because that's how many carbons it has. So it must have 2 times 8 plus 2 hydrogens, which gives us 16 plus 2, or 18. So its molecular formula would be C8H18. Before we finish, we just need to mention that one of the key features of alkanes is that they're saturated compounds, which means that every carbon atom has 4 single covalent bonds. There aren't any double bonds. For example, if we were to take this molecule of propane and change one of these single bonds to a double bond, then each of the carbons involved would have to lose a hydrogen, and what would have left would no longer be an alkane. Instead, we would class it as an alkene, which we'll see when we take a look at cracking hydrocarbons in a later video. In our next video though, we'll stick with alkanes by taking a look at their properties and seeing how to write equations for their combustion. Anyway, alkanes are a homologous series of hydrocarbons that contain only carbons and hydrogen atoms, with no double bonds. And we covered the names of the first 4 alkanes in the series. In this video though, we're going to talk about the properties of alkanes, and then see how we can write equations for their combustion. Although all alkanes have similar properties, there are trends that you need to know about as the length of the carbon chain increases. The first is that the boiling point increases with chain length. So these four here all have fairly low boiling points, and so exist as gases at room temperature, because they have the shortest chains. However, longer alkanes, with more than 4 carbons, are liquids at room temperature. And if the chains are really long, then they could be solid. This feature actually explains their next property as well, which is that shorter alkanes are more volatile, meaning that they evaporate more easily, because of that low boiling point we just talked about. Meanwhile, longer alkanes are more viscous, which just means that they're kind of thick and sticky, like honey. The last property you need to know is that shorter alkanes are also more flammable, which means that they're easier to ignite or burn, as we'll see when we come to crude oil. The next thing we need to look at is combustion reactions. One of the main uses of hydrocarbons, like alkanes, is for fuel, because they release loads of energy when they're burned with oxygen. As long as there's enough oxygen available, we get complete combustion, which is when a hydrocarbon reacts with oxygen to form carbon dioxide and water, releasing loads of energy in the process. So we could say that it's an exothermic reaction. We could also say that the hydrogen and carbon in the hydrocarbon are being oxidized, as each of the elements is combining with oxygen to form CO2 and H2O respectively. Now, when it comes to exams, you need to be able to write out the equations and balance them. For example, you could be asked to write the balanced equation for the complete combustion of propane. We saw earlier that propane is C3H8, so we'll react this with O2 to form CO2 and H2O. Then all we need to do is balance it. We know that on the left we have 3 carbons, so on the right we'll need 3 CO2s. We also have 8 hydrogens on the left, so because each H2O molecule contains 2 hydrogens, we know we'll need 4 of them on the right. Then lastly, we need to balance the oxygens. On the right, we now have 6 oxygens in the CO2s, plus 4 oxygens from the waters, so 10 in total. So to get 10 on the left, we'll need 5 oxygen molecules. And finally, we just need to double check that all the numbers balance, which they do, so we're done. As a last example, let's write the balanced equation for the combustion of nonane, which has the molecular formula C9H20. The first step is to write out the unbalanced equation. Then, because nonane has 9 carbons, we know that there will be 9 CO2s on the right. And as it has 20 hydrogens, we'll have to form 10 H2Os. Then lastly, we just need to balance the oxygens. So there's 9 times 2, or 18, in the carbon dioxides, and 10 in the waters, which is 28 in total. So on the left, we must have 14 O2 molecules, because that totals 28 oxygen atoms. And that's it, our equation now balances. The key point to take away from this video is that the properties of hydrocarbons, like alkanes, depend on the length of their carbon chain, with the shortest hydrocarbons having the lowest boiling points, and so being the most volatile and flammable, which makes them great fuels. And whenever we use a hydrocarbon as a fuel, we call the process combustion, with complete combustion only taking place if there's enough oxygen available, which will produce carbon dioxide and water, releasing loads of energy in the process. Anyways, into its different components, using fractional distillation. Crude oil is a fossil fuel that we get from deep under the ground. and is basically a mixture of lots of different compounds. Nearly all of these compounds, though, are hydrocarbons, which contain only hydrogen and carbon. And the most common type of hydrocarbons are alkanes, which we covered in the last couple of videos. Now, crude oil is formed naturally from the remains of dead plants and animals, particularly plankton, that died millions of years ago and were buried in the mud. Then, in the millions of years between then and now, the high pressures and temperatures under the ground turned this organic biomass into crude oil. As it formed, this crude oil soaked into the rocks and was stored for millions of years. But we can get it back out by drilling into the rock and sucking it up to the surface. As crude oil takes so long to form, it's effectively a finite resource. And if we continue to extract and use it at the rate that we are now, then one day we'll run out of it completely. This is why we refer to fossil fuels like coal, oil and gas as non-renewable fuels. Once we've extracted the crude oil from the ground, we need some way to separate out all of the different hydrocarbons in the mixture, because they each have different properties, and so we'll use them for different things. To do this separating, we use a process called fractional distillation, which involves heating the crude oil up and separating out the different compounds by making use of the fact that the different compounds all have different boiling points. The first step is to feed the oil into a chamber and heat it until most of it has turned into a gas. We then pass this gaseous mixture into a fractionating column, which is really hot at the bottom, but gets cooler towards the top. The idea is that these hot gases will then start to rise up the column. But importantly, as soon as they reach a region that has a lower temperature than their boiling point, they'll condense into a liquid. The hydrocarbons with the longest chains, so the most carbons, have the highest boiling points, and so they'll quickly condense back into a liquid and drain out of the column early on, because it's not hot enough to keep them in their gaseous states. These are things like bitumen, which we use to surface our roads, and heavy fuel oil, which can be separated further and used for things like heating oil, fuel oil, or lubricating oil. The shorter chain hydrocarbons, though, have much lower boiling points, so they'll stay as a gas for much longer as they rise up the column until they finally reach a cool enough temperature that they condense into a liquid. This gives us fuels like diesel and petrol, which we use in cars and other road vehicles, and kerosene, which is used in jet engines. Some hydrocarbons, though, are so short and have such low boiling points that they stay as a gas the entire time. For example, LPG, which stands for liquefied petroleum gas, contains mainly propane and butane, which are both very short-chain alkanes. If we compare these different groups or fractions, the ones towards the top, which are the shorter chains, are the most flammable, and so they tend to make the best fuels. Meanwhile, the longer chain hydrocarbons, here at the bottom, are often poor fuels, so are instead either used for something else, or can be broken down into smaller hydrocarbons in a process called cracking, which we'll take a look at in the next video. The last thing to point out is that as well as all of these fairly direct uses that we mentioned here, petrochemicals, which is what we call all of these substances that we get from crude oil, can also be used as feedstock, which just means raw materials for the petrochemical industry. You use them to make things like solvents, lubricants, polymers, and detergents. Anyway, that's all for this video. that we can think of crude oil as a mixture of lots of different hydrocarbons, and that we can separate out these different hydrocarbons by the length of their carbon chains, using a process called fractional distillation. We also saw that the shortest hydrocarbons are the most flammable, and so they make the best fuels, whereas the longer chain hydrocarbons are thick, viscous liquids, which makes them comparatively less useful. So in today's video, we're going to look at how these longer, less useful hydrocarbons can be broken down into shorter, more flammable hydrocarbons, in a process we call cracking. Now, cracking is a thermal decomposition reaction. And if you think about that word, thermal means heating, and decomposition, or to decompose, means breaking down. So thermal decomposition means breaking down molecules by heating them. And there are actually two different methods you need to know about. One is catalytic cracking, and the other is steam cracking. Regardless of which one of these we're going to do though, the first step is to heat our long-chain hydrocarbons and vaporize them, which just means to turn them into a gas. Then if we were using catalytic cracking, we would have some hot powdered aluminium oxide ready as our catalyst. We'd then pass our hydrocarbon vapor over the powder, and as the long hydrocarbons come into contact with the catalyst, they'd split apart into two smaller hydrocarbons. On the other hand, for steam cracking, once we've vaporized our hydrocarbons, we mix them with steam, and then we heat them to a very high temperature, which again causes the long hydrocarbon chains to split apart into shorter ones. Now, as well as knowing these different types of cracking, you also need to be able to write balanced chemical equations for the cracking of long-chain alkanes. The equation for this is that you take your long-chain alkane, for example decane, and it will go to form a shorter alkane molecule, like heptane, and an alkene, which in this case would be propene. The important thing to remember here is that the number of carbons and hydrogens on each side has to be the same, just like with any other balanced equation. So as decane is 10 carbons long, and one of the products is heptane, which has 7 carbons, then our other product must have 3 carbons. And if you did the same thing for hydrogens, you'd find that there aren't enough hydrogens left for both products to be saturated and have all single bonds. So instead, one of our products has to have a double bond, which is what makes it an alkene rather than an alkane. Instead of being a waste product though, these alkenes can be used to produce polymers, and also be used as starting materials for producing loads of other chemicals. Let's now have a look at a proper example. Decane, C10H22, can be cracked into ethene, C2H4, and one other hydrocarbon. Write a balanced equation for this reaction. So the first thing we do is write the equation with everything that we know so far. So decane goes to form some unknown alkane plus ethene. Then all we have to do is work out how many carbons and hydrogens our unknown alkane must have. To do this, we just take away the number of carbons and hydrogens of our known product, ethene, away from our reactant, decane. And whatever's left is the number of carbon and hydrogen atoms our unknown alkane must have. So 10 minus 2 carbons means that our alkane must have 8 carbons, and 22 minus 4 hydrogens means our alkane must have 18 hydrogens. So its formula is C8H18. And so we just write that into our equation. Now, before we finish, we just need to point out that alkenes are another example of a homologous series. So a group of similar compounds with similar properties, just like alkanes are. And the only structural difference between these two groups is that alkenes have a double bond, while alkanes only have single bonds. So we can say that alkenes are unsaturated, while alkanes are saturated. And this difference leads to two important features of alkenes. One is that they're more reactive than alkanes, so they're able to react with bromine. And specifically, you need to know that if we add bromine water to a solution of alkenes, then they'll decolorize the bromine water from orange to colorless. And this is actually the test for alkenes that you need to remember. The other feature of alkenes is that they can be added together to make polymers, because the double bonds can break to form two more bonds, and so they can bond to the adjacent molecules. Anyway, so we'll cover their structure and bonding, how to draw them, and why they're solid at room temperature. Now, polymers are a huge and diverse group of different substances, and they make up all sorts of things. What they all have in common, though, is that each polymer molecule is made up of lots of smaller units called monomers. For example, polypropylene is one of the main polymers in plastic, and a single molecule can be thousands of atoms long. But it's actually made from these monomers, called propene, which have the formula C3H6. And if we line a few of them up, you can see how they could keep adding together again and again until they form a huge polymer chain. Now, the important thing to be able to do is notice that a particular molecule could be a polymer, and identify the repeating monomer. For example, we can tell that this polypropylene we just made could be a polymer because we can pick out a small section that seems to repeat. Then, once we've identified this repeating unit, we can draw it out by itself. And you'll often see the letter N in the bottom right corner, which represents how many of those repeating units there are in the overall polymer. So if we wanted to write a reaction for combining 400 propene monomers, then instead of drawing out the entire polymer as a product, which would take us ages, we could just draw the repeating unit and put 400 in the corner. In general though, we just put N instead of actual numbers. The other thing to notice with these repeating units is that we always use curved brackets, and we show the bonds coming through the brackets. Now, the last thing we need to look at is the melting and boiling points of polymers. The bonds within the polymers are all covalent bonds, which are really strong, and so would require really high temperatures to break. However, to melt or boil polymers, it's not actually these covalent bonds that we need to break. Instead, it's the intermolecular forces between the separate polymer molecules. And these intermolecular forces are much weaker than covalent or ionic bonds. However, because the polymers are so long, they have a high surface area, and so there are loads of these intermolecular forces, which means that to break them all would still require quite a lot of energy. So, although polymers have lower melting and boiling points than giant covalent structures like diamond, or giant ionic structures like sodium chloride, they do have higher melting and boiling points than simple molecular substances like oxygen or chlorine, which only have a few of these weak intermolecular forces between each molecule. And this is the reason why polymers are generally solid at room temperature. As we said earlier, there are loads of different types of polymers, and two of the main ones are addition polymers and condensation polymers, which we'll take a look at in other videos. That's all for now though, so thanks for making addition polymers using alkenes, with a focus on how to draw the monomers, the repeating units, and the polymers. The feature that makes a molecule an alkene is the fact that it has a carbon-carbon double bond. Like we can see here between the two carbon atoms in this ethene molecule. Because of this double bond, we say that alkenes are unsaturated. And under the right conditions, the double bond can break into a single bond, which allows the two carbons to form new bonds with something else. So if we had 3 ethene molecules, and all of the double bonds opened up, then they'd be able to form new bonds with each other, and so combine to form one long chain, which we'd then call a polymer. Now, one way to represent this reaction would be like this, where we show all the ethene molecules, which are our monomers, on the left, and draw out the entire polymer that they form on the right. The problem with this technique, though, is that these reactions can sometimes involve hundreds of monomers, so to draw out all of them would take forever. A better way to do it is like this, where we show a single monomer on the left, and a single repeating unit of our polymer on the right. And when we say repeating unit, all we mean is the group of atoms that are repeated throughout the polymer, and contain exactly the same group of atoms as are in the monomer. So in this case, 2 carbons and 4 hydrogens. When it comes to writing out these equations yourself, there's a few points that you need to remember. One is that you need to draw the bonds of the monomer facing up and down rather than out at angles. And on the repeating unit, you need to draw these empty bonds pointing out to the left and right that go through the bracket. The other important feature are the ends, which represent how many of the monomers, and thus how many repeating units, there are in the reaction. For example, if N was 10, then that would mean that there were 10 ethene molecules on the left, and so the polymer would be 10 repeat units long. To put all of this together, let's try and write an equation for the addition polymerization of butene, which is this 4-carbon alkene. The first thing we need to do is redraw the butene, so that it's in the same format as this diagram of ethene that we just saw. To start, we need to identify the double bond, which is here between the first 2 carbons. Next, we need to arrange all of these atoms as separate groups, because they're the groups attached to the carbons of our carbon-carbon double bond. And if we look back at our ethene example, we need to place them directly above and directly below the 2 double-bonded carbons. To do this for butene, let's start with our 2 double-bonded carbons, and then we'll rearrange each of the separate groups one by one, so that it's easy to follow along with what's happening. This first hydrogen needs to change from being shown sticking out at an angle to being shown like this, pointing straight up from the carbon. And we do exactly the same thing for this hydrogen, so that it points straight down rather than sticking out at an angle. Then this hydrogen over here is already pointing straight down, so we just redraw it exactly the same way. Finally, for this big group on the right, we use a little trick and simplify it before moving it about. To do this, we just count up all the carbons and hydrogens and write them out in shorthand. So because there are 2 carbons and 5 hydrogens, we write this group as C2H5. And then we just do exactly the same thing as before, and rewrite the group so that it's directly above our double-bonded carbon. One thing to be aware of, though, is that it's important that this bond is drawn going from carbon to carbon, rather than to the H5 part. Now that it's drawn in the right format, we can add the brackets and put the N in front of it. Next, we can draw our reaction arrow, and then draw the other side of the equation that shows the repeating unit. We draw pretty much exactly the same thing, but notice that we've taken out the double bond and instead put the carbon's bonds out to the sides, extending through the brackets. And remember, for a repeating unit, the N goes here on the bottom right, just outside the bracket. The last thing we need to cover is how to name the polymers, which is actually really easy, because all we have to do is put the word poly in front of the monomer's name, and put the monomer's name in brackets. So in our example here, where we're drawing the polymer of butene, the monomer is butene, and therefore the polymer is called polybutene. Or if we go back to the first example we did, the polymer would be called polyethene. Or if we had this monomer, which is called chloroethene, we'd make the polymer polychloroethene. The very last thing we need to mention is that these addition polymerization reactions require high pressures and a catalyst to work. So you might sometimes see pressure and catalyst written on the reaction arrow. You don't have to put this on the arrow yourself, but you might be asked for these two conditions. Anyway, that's everything for this video, so hope that all made some sense, and cheers for making it through to the end.